Olá, pessoal. Boa tarde a todo mundo. Bem-vindos todos a mais um webinar Luiz Carlos de Lima Silveira, aqui pelo programa de pós-graduação em Neurociências e Biologia Celular. Então, para quem não conhece, esse webinar ele é uma atividade do programa de pós-graduação em Neurociências, que é em homenagem ao professor Luiz Carlos de Lima Silveira. Deixa eu tirar aqui o áudio. É uma atividade do programa, né, em homenagem ao professor Luiz Carlos de Lima Silveira, e que a gente sempre tenta trazer uma pessoa de destaque na produção científica de alguma área dentro de neurociências e biologia celular, para que ele possa dar uma palestra para a gente e depois possa abrir para conversar conosco a respeito dos tópicos mais interessantes de neurociências que a gente pode ter no mundo. Hoje, pessoal, a gente vai ter o prazer de trazer para conversar com a gente o professor Rodger Elble. Ele é professor da Universidade de Illinois do Sul. Ele é um dos pesquisadores mais renomados na área de motricidade humana, especialmente com o tópico para análise do tremor. Já está há mais de 40 anos estudando esse tópico. A partir de agora, eu vou falar em inglês. Eu conversei já com o professor Elble para também, quando for falar de forma pausada, para facilitar a compreensão de todo mundo, e a dinâmica é aquela mesma de sempre. Após a palestra, quem quiser fazer perguntas, pode colocar no chat que eu pergunto para ele. So, I would like to invite to our lecture room, to our lecture, the Dr. Rodger Elble from Southern Illinois University. And Dr. Elble is one of the more prominent researchers in human motricity, especially in the field of tremor in physiological and pathological conditions. Professor Rodger Elble, thank you very much for coming to join with us today. And we are very happy to have you here and to share with you this moment and discussion about tremor. Thank you very much.
Thank you. So can you see my screen now?
Yes, your screen is okay.
Okay.
Okay. You can start. I will remove my image and you can begin. Thank you.
Okay. Well, thank you. It's a pleasure to speak to you today. I'm 75 years old now, but I can actually remember when I was a student, and I'm very pleased to be speaking to some students today. I'm from Illinois, and this is where Illinois is in the United States, if you haven't been there. It's close to Chicago. Many of you have probably been to Chicago. And I've been studying tremor with motion transducers since 1972. I was a graduate student, a combined degree MD, PhD student under Jim Randall, who was also an engineer. So we were both trained in engineering at Purdue University and then met at Indiana University, where I did my graduate school work in physiologic tremor. What we're going to cover today is the use of motion transducers and EMG in tremor analysis. I'm also going to touch on the use of coherence analysis and its interpretation in the context of tremor. And I'm also going to mention a little bit about quantification of tremor rhythmicity and address the issue of diagnostic usefulness of rhythmicity measurements. Everything that I will say today is basically contained in these two review articles that were published in the last 2 years. So I strongly recommend the article by Deutschel and colleagues in Clinical Neurophysiology last year, and then the review article by Mark Hallett and co-authors, same journal, the previous year. So To begin, electrophysiologically, there are two mechanistic forms of tremor that can be defined electrophysiologically. Now, of course, there are many forms of tremor, many types of tremor disorders that I don't have enough time to review today. But for the most part, these tremor disorders fall within two categories defined electrophysiologically. Central neurogenic tremors are produced by oscillation somewhere within the central nervous system. And we can identify this type of oscillation because the frequency of the oscillation is not a function of limb mechanical properties or the reflex loop time. By contrast, mechanical reflex oscillation has a frequency that is a function of limb inertia and stiffness, and also a function of the reflex loop time. Now, this could be the segmental stretch reflex, or it could be a stretch reflex that involves transcortical pathways. Now, most, but not all, central neurogenic tremors, such as Parkinson tremor and essential tremor and dystonic tremor, involve this pathway shown in the red lines. The cerebral cortex projects down to the pre-cerebellar nuclei, which of course project to the cerebellum. The cerebellum then projects back to the, or out to the contralateral ventrolateral thalamus. And then there's a reciprocal connection between the thalamus and cerebral cortex. And that's shown in this sagittal view of the brain, this MR in the lower right-hand corner. So this is these are the anatomical pathways of this cortical bulbo cerebello thalamocortical loop. And note, and I can't overemphasize that there are reciprocal connections between the cortex and the thalamus. And all of these connections, each arm of this network is excitatory. So if you model this network, it is very oscillatory, tremorogenic. And exactly why this network would be made in this way is really somewhat unclear, but suffice it to say that it's conducive to oscillation no matter where the oscillation originates, and is involved in most forms of tremor. There are tremors, however, in particular cerebellar intention tremor that involve that involve long loop reflex pathways shown here in blue, where peripheral sensory feedback feeds through the thalamus to cerebral cortex and back down to the periphery. And that type of oscillation would have a frequency that's dependent on limb mechanical properties, namely stiffness and inertia. So that's shown in this schematic diagram. So this is physiologic tremor. In physiologic tremor, the muscles, the motor units during postural tremor, fire randomly. They are not synchronized. So there's no rhythmic modulation of EMG activity. And so just for simplicity's sake, I show three muscles here. They all have input from the spinal cord. And if you look at the EMG shows no evidence of rhythmic modulation at the frequency of physiologic tremor. And if you compute the power spectrum of the rectified filtered EMG, it's flat, shown here in red. If you record the force produced by these muscles, the force has a so-called 1/F profile, so-called pink noise profile, and that is produced by the, excuse me, by the frequency response characteristics of skeletal muscle, which are shown here in this red curve. This is a so-called Bode plot, and this is on a log scale, and right here is 3 hertz. So most skeletal muscle, for example, in the limbs, has a cutoff frequency, a low pass filtering frequency of about 3 hertz or even less. So it's going to attenuate high frequency irregularities and will pass through low frequency activity. And most voluntary movement is below 3 hertz. Now the joint mechanics have these viscoelastic properties. The spring and inertia are conducive to oscillation as long as the viscous damping, the friction and damping within the muscle or within the joint is low enough. And that's shown here. These Bode plots, the green and blue, are Bode plots for 2 different, for the same joint with 2 different inertial loads. And so if you add inertia, the frequency goes down. But you can see how depending upon the natural frequency of the joint, you will also attenuate higher frequency oscillation and have resonance in the vicinity of the natural frequency. This can be, or has been, modeled very nicely. It can be modeled by a second order differential equation shown here. My mentor, Jim Randall, used actual physiologic tremor recordings with an accelerometer to estimate the parameters of this model. And he found that the damping ratio for the wrist is about 0.1, so it's an underdamped system. And the frequency is somewhere between 8 and 10 hertz. And you note that the natural frequency is proportional to the square root of the stiffness, which is K over the mass. And this is actually the power spectrum of this model solved with MATLAB. So this looks like a real tremor recording, physiologic tremor recording, but it is not. It's a artificially produced recording by this model solved with MATLAB. But this is an actual recording, and you can see the similarities. The black curve is without mass loading, and this is the wrist. So the accelerometer is on the back of the person's hand. The forearm is supported by the tables, and the hand is splinted so that motion is restricted to the wrist. And that's really important because the different joints have different natural frequencies. And as you can see on the right, the rectified filtered EMG spectrum is statistically flat. Physiologic hand tremor recorded in this manner has an amplitude, a mean amplitude of 0.1 millimeters. So it's very small. At that level of movement, the stretch reflex receptors, the spindles and tendon organs, they are sensitive to this level of oscillation, but it's not enough. There's not enough stretch reflex modulation to affect the motor neurons in the spinal cord. So there's no reflex modulation of the motor neurons, and that's why you get a flat spectrum. In addition to the irregularities in muscle contraction, another source of energy to our body producing physiologic tremor is cardioballistics. Every time your heart beats, there's a stroke volume of blood, and this produces an impulse to the body that can be detected by sensitive motion transducers. And in this case, the motion transducer is on the person's head, secured by this harness. And we record EKG. So these are the QRS complexes. And you can see that following each QRS complex, there's this transient oscillation. And that oscillation occurs at the natural frequency of the of whatever body part that you're recording from. In this case, the head. So the natural frequency of the head and neck is down around 2 to 3 hertz. For the wrist, it would be 8 to 10 hertz. If I paralyze all of the muscles in my body, I will still have some physiologic tremor, but it'll be purely rest tremor, of course, because the muscles are paralyzed, and that will be solely due to this cardioballistic oscillation. So what happens when the stretch reflex is somehow enhanced by anxiety or fatigue, or maybe medications that we've taken, stimulant medications like for a cold? What happens then is that the somatosensory feedback increases enough to entrain the motor neurons and cause the different muscles involved to fire coherently at the frequency of the mechanical oscillation, at the natural frequency. So we still have cardiac systole contributing, but it contributes very little in percentage terms. Most of the forcing comes from either irregular muscle activity or rhythmic muscle activity when there is enough somatosensory feedback. So when the muscles are modulated by somatosensory feedback, we call this enhanced physiologic tremor. And that is shown here with the accelerometer. Now, again, when we add mass, the frequency goes down approximately 3 hertz. But now the EMG, instead of being flat, has this spectral peak in the unloaded state, which is in black, with no added mass. The frequency is about 9 hertz, and then the frequency decreases down to around 7 hertz when a 300-gram load is attached to the back of the hand. So we call this mechanical reflex modulation because the frequency changes. It's a function of limb mechanics. It's not a constant frequency as you would expect from a central neurogenic oscillation. But there is a central neurogenic component of physiologic tremor, and this component is generally very difficult to record from most normal people. It just so happens that I have a very prominent 8 to 12 hertz component. So when I was a graduate student, I got lucky and was able to record this very easily from my own forearm. But many people that participated in my studies, such as my mentor, Jim Randall, had almost no 8 to 12 hertz component. It took a lot of fatiguing and various stressors to make this evident. So if you record from a lot of normal people, most people will simply have this pure mechanical oscillation with a flat EMG spectrum. about 2/3 of all people. About 25%, most of the remainder, will have a peak in the EMG either with loading or without loading, but not in both cases. So we call this an equivocal type of analysis. We're not really sure that it's mechanical reflex or if it's central neurogenic, if we can't record the EMG in both. When you see this modulation in both, and when the frequency decreases in amplitude, then you know that you have an enhanced physiologic tremor. And it's uncommon enough that you should look for etiologies other than just anxiety or fatigue. Medications can do this, such as any kind of stimulant medication. And then the 8 to 12 hertz component is readily recorded from less than 10% of normal people. So most people have this pure mechanical resonant oscillation. And when you look at their EMG, it's more or less a smooth interference pattern with these irregularities in amplitude that provide this broad spectrum forcing. Now, what happens in pathologic tremor? That's shown here. And a young man who at age 17, he comes from a large family of people with essential tremor, which is the most common form of pathologic tremor. Essential tremor patients shake in their arms and often in their head and voice, but they have no other abnormalities. And initially, when I recorded his tremor, he had this wrist tremor peak at the physiologic tremor frequency of 8 hertz, but there was also some modulation in his EMG. So here's the EMG in red, here's the wrist oscillation, the accelerometer, and you can see both of them have peaks. When I added mass, the peak in the EMG went away. So this is one of those equivocal situations. But he came back 6 years later and said, well, I think I'm getting grandma's tremor. And lo and behold, he had this very prominent modulation in the EMG at a slightly lower frequency. And when you added inertial load, 300 grams, notice that the frequency did not change at all. And yet there's still this mechanical resonant peak. The two oscillations are actually superimposed in the unloaded state, and then they separate with mass loading. And notice now the coherence between EMG and acceleration are very strong, suggesting that the muscles in the forearm are being very strongly entrained by this abnormal oscillation called essential tremor. So how about an example of mechanical reflex oscillation? So this young lady had a stroke. And when you see her, you're going to be surprised that she had a stroke. She had a whiplash injury of her neck. And about 70 days later, she developed this intention tremor. Her initial deficit when she had this injury was numbness on the right side of her body. She had nausea and vomiting, and she had disequilibrium or bad balance. And the MR scan showed a very clear stroke in the ventrolateral thalamus, very close to where we put electrodes for deep brain stimulation. What's interesting about her tremor, these are the recordings from her hand with an accelerometer. When she simply extended her hand and did not point at anything, just aimlessly extended her hand, she exhibited normal physiologic tremor, shown here in red. and which corresponds to the axis on the right side. So very normal tremor. But then when she pointed at a target, the tremor increased dramatically. So she has visually guided intention tremor, much greater in amplitude, a lower frequency, but still when you added mass, the frequency decreased. So this is an example of a pathologic form of mechanical reflex oscillation. And this is very similar to the tremor that you see in monkeys when you produce a lesion in the deep cerebellar nuclei. Whoops. So we know from studying various forms of pathologic tremor in this manner that essential tremor, Parkinson tremor, orthostatic tremor that I'll show you in a little bit, dystonic tremor, the three most common forms of tremor are essential tremor, Parkinson tremor, and dystonic tremor. And they're all centroneurogenic and come from this cortical bulbo cerebello thalamocortical loop. Examples of mechanical reflex oscillation are physiologic tremor, enhanced physiologic tremor, patients with cerebellothalamic lesions, like the little girl that had the stroke in her thalamus, and also patients with reflex cortical myoclonus. They also have tend to have oscillation that occurs has a frequency that is a function of limb mechanics and reflex loop time. But there's more to that story, and I don't really have time to get into that. Now, a little bit about where you put these accelerometers. So in the preceding studies, I restricted motion to the wrist. But notice that if I allowed the entire arm to extend horizontally, I could have oscillation from the wrist, from the elbow, or from the shoulder. And they all have different natural frequencies. The wrist natural frequency is 7 to 10 hertz. The elbow is 3 to 4 hertz. The shoulder is about 2 hertz. So it will depend greatly where the tremor is coming from. And this has been a problem with various studies that have been published in the literature. Another point that I'd like to make here is that the old accelerometers that I used when I was a student really no longer exist. They were subject to gravitational artifact and were generally uniaxial. Later on, they became biaxial and triaxial. But they were very cumbersome to use and very expensive. Now, your cell phone has an accelerometer. Lots of devices have accelerometers, and you can buy inexpensive motion transducers. This XSENS dot cost me $150. And it has a 3-dimensional accelerometer, triaxial gyroscope, and triaxial magnetometer. And it also has a fusion algorithm built into it, which fuses these 3 signals mathematically, computes the gravitational artifact, the instantaneous gravitational artifact, and subtracts it from the accelerometer signal. So you get pure inertial acceleration uncontaminated by gravity. And this is very important when you're estimating, trying to estimate motion and position in space. This becomes even more important when you do complex tasks like finger, nose, finger movements. You can put an accelerometer out here on the hand, shown here in green, but once again, motion can occur at the wrist, it can occur at the elbow, it can occur at the shoulder. And really to comprehensively study these types of multi-joint movement, you need multiple transducers, at least one of these inertial measurement units on each segment of the limb. And it is good also to have EMG on one or more muscles. So this kind of illustrates, this is a lady with bad essential tremor. And you can see she has very bad tremor, disabling tremor. She underwent deep brain stimulation. I have the device turned off now just to show you. And in a moment, I'm going to put a 1 kilogram weight in her hand. And you say, well, the frequency didn't change. I showed the power spectrum of the gyroscopic transducer with and without inertial loading. And the frequency didn't change, but I really didn't load a single joint. So it's really not a valid test. When you look for changes in mechanical properties, the effect of changes in mechanical properties on tremor frequency, you have to really restrict motion to one joint. This tremor network, this cortical bulbocerebello-thalamocortical loop, is involved in so many tremors, and yet only in Parkinson's disease do we think we know where the oscillation originates. We think the oscillation actually originates in the basal ganglia loop, the globus pallidus and subthalamic nucleus. And then this oscillation gets into this so-called tremor loop, which I told you earlier is very prone to resonant oscillation. And once the Parkinson tremor oscillation gets into this loop, it is amplified. And that explains why Parkinson tremor can be suppressed by lesions or a deep brain stimulation electrode in the ventrolateral thalamus, but also in the subthalamic nucleus and in the globus pallidus interna. Of all these other types of tremor, except rhythmic cortical myoclonus, we don't know where the origin of the oscillation is. In rhythmic cortical myoclonus, we know that it's hyperexcitability of the cerebral cortex. And the cerebral cortex starts firing rhythmically at frequencies ranging from about 7 to 18 hertz. So a wide range of frequencies, very irregular. And what appears to happen is that this broad spectrum firing of the burst firing of the cortex then is tuned or entrained more finely frequency tuned by this loop shown in red, but also in the transcerebral spinal cortical reflex pathways. So limb mechanics have a role there as well. So this is the critical question in tremor research now. What is this network doing for each type of tremor? Is it controlling tremor or trying to control tremor, or is it actually causing tremor? And I refer you to a lot of nice work done by Rick Helmick in the Netherlands. And he's also the co-author in one of the two papers that I introduced at the beginning of my talk. So we have many tools for defining these networks, these oscillatory networks. We have the neuroimaging tools, positron emission tomography, SPECT, functional MRI, diffusion tractography. But these tools cannot be correlated with tremor in real time, whereas EEG, MEG, magnetoencephalography, and of course, intraoperative recordings with microelectrodes can be recorded with tremor in real time. And when we do this type of analysis, when we try to record peripheral tremor and central activity simultaneously and determine whether they're related, we do some coherence analysis. And so I'd like to say just a word about the limitations of coherence analysis. You can have very coherent activity between two recordings without there being any tremor at all. So, for example, in physiologic tremor, theoretically, if it was produced by one muscle only, even though the spectrum is totally random, it would still be coherent with the mechanical resonant oscillation recorded with an accelerometer. However, the wrist is not controlled by one muscle. It's controlled by at least 7 muscles in the forearm. And all of these could be contributing random activity to the wrist. And the coherence then would be some fraction of 1. Coherence is basically a measure of correlation squared, or it's proportional to the amount of variance that is explained by some linear relationship between two recordings, 2 signals, 2 time series, such as muscle, EMG, and accelerometry. So if we go back to these graphs that I showed you earlier, notice that in this case, when the young man at age 17 had no rhythmic modulation of EMG in one of his extensor forearm muscles, he still had the mechanical resonant oscillation, and the coherence is only about 0.2, very low. And that's basically what you would expect if all the muscles are firing randomly and independently, because there are 7 muscles, so 1/7 of 1 is 0.14, roughly 0.14, 0.15. So that's exactly what you would expect. The fact that the coherence is so high in essential tremor indicates that all of these muscles of the forearm have become entrained more or less into a single oscillation. And that's an important concept, because the same concept applies to the recording of nerve cells in the brain, or micro oscillators in the brain. The more they're entrained, the stronger the coherence will be between whatever brain source you're looking at and the peripheral EMG. And so that is modeled here schematically. So now we have our 3 muscles. We still have our joint. Cardiac systole is contributing, but very small amount of overall input. Now we have sensory feedback that goes not only to the spinal cord, but also to our tremor loop, our cortical bulbo cerebello thalamocortical loop. And we could have entrainment by virtue of the sensory feedback, and we could also have entrainment by virtue of coupling within this loop by the resonant properties within the loop that I mentioned earlier. Remember that all arms of this loop are excitatory, and also within the spinal cord. So there are all sorts of sources of entrainment and the more entrainment that you have, the stronger the tremor is going to be and the more rhythmic it's going to be. So here is the most rhythmic, coherent tremor known to man. The video is actually running, so you say, I don't see any tremor. I don't see his legs shaking. And that's because the frequency is very high. It's around 16 hertz, close to it's 15.5 hertz in this man. And his legs are very heavy, so the inertia of the mass, the moment of inertia of his legs is very high. And so the mechanical properties and the EMG properties filter out this high frequency oscillation and attenuate the amplitude. But the rhythmicity is still very high. And what these patients complain of usually is they don't complain that their legs shake. They complain that they feel off balance when they stand. And many patients cannot stand for very long because they become increasingly unsteady. They have the sensation of unsteadiness. On the left-hand side, these black and red curves are the EMG spectra for the vastus lateralis on one side and the triceps brachii on the other side. So to record this, what I had this man do was stand and lean against the wall using his hands. And so his arm muscles and his leg muscles were activated. And you can see that the coherence is almost perfectly one. Very strong coherent activity between the arm and the leg. And also, this is also true for coherence between one side of the body and the other. And there is no other tremor that does this, produces this extremely strong coherence among multiple body parts, both on the right and the left. And you can record this in the EMG lab very nicely. So as you can see on the screen, you see more or less a normal interference pattern from the vastus lateralis. But when he stands up, you'll see this interference pattern change to rhythmic bursting at the frequency of tremor. So you notice that the sound changed too. It changed from a kind of a white noise sound to a rhythmic sound that is similar to the sound of a helicopter, and this is called the helicopter sign. If you record from using high resolution EEG, if you record from patients, when during the first 15 seconds, both cerebral hemispheres are very strongly coherent. So the coherence here's the bar. So red is 0.8, which is a high coherence. Keep in mind that this is coherence between the brain structures and the peripheral EMG. Now, the signal-to-noise ratio is not as good in deeper brain structures, such as the brainstem, the cerebellum, and the thalamus, but still statistically significant. Notice that for the first 15 seconds, the two cerebral hemispheres are coherent with each other, and then afterward, the cerebral hemispheres become incoherent. They're no longer coherent with each other. And this seems to correspond to the onset of the sensation of unsteadiness that these patients have. Since the tremor in the body is coherent on both sides, remains coherent, it's not clear why the brain suddenly decides that these signals are not coherent. So the brain is clearly not processing this oscillation correctly. Now, the last thing I'd like to touch upon is rhythmicity. And I just mentioned that the most rhythmic tremor known to man is orthostatic tremor. There are other types of tremor, such as Parkinson tremor, dystonic tremor, and essential tremor, that are frequently difficult to distinguish clinically, And various investigators have recorded tremor with motion transducers and then computed the rhythmicity of the tremor. Of course, a perfectly rhythmic tremor would have a spike in the power spectrum at a single frequency. But normally the spectral peak has some bandwidth due to variability in the frequency. And so you could conceivably compute the half power bandwidth. The more narrow it is, the more rhythmic the tremor is. So this would be a less rhythmic tremor. And this is commonly done in studies of this type and is used in engineering routinely. There are some other measurements that have been devised. One is to compute the cycle-to-cycle variability and tremor frequency, the instantaneous frequency, and then look at the interquartile range of differences in successive cycles. And we call this the tremor stability index, and that was published by DiBiase. The problem is he and his collaborators concluded that this is useful, very useful in distinguishing Parkinson tremor from essential tremor. But he did not control for amplitude, tremor amplitude. And tremor amplitude is, if you think about it, an indirect measure of entrainment within the nervous system. To get a tremor of bigger amplitude, you have to have greater entrainment of the networks involved. And so what I have done with my own data, and I've worked with others, collaborators, we've looked at various data sets, and we computed this tremor stability index. We've also computed the half power bandwidth, the cycle-to-cycle standard deviation in tremor frequency, and also the approximate entropy. And all of these so-called measures of rhythmicity are a function of amplitude. So here's essential tremor in Parkinson in orange, essential tremor in blue, and you can see that there's a clear relationship with amplitude. This is displacement of the hand. Basically, the tremor stability index decreases, meaning that there is less cycle-to-cycle variability with greater amplitude. And that's what you would expect with greater entrainment of the neural networks. The motion transducers are finally very good at quantifying tremor, but again, you have to consider where the tremor is coming from. So if I put an accelerometer on the hand, it's not going to record finger tremor, except very indirectly by vibrations transmitted from the fingers back to the corpus. If I put this accelerometer back here on the forearm, it's not going to record wrist tremor or finger tremor. And yet people make this mistake all the time. And I'll show you this recording. This is a man with very bad essential tremor. This is with this stimulator on. You can see that in this posture, the oscillation is coming primarily from the shoulder, and to a lesser extent the elbow, and almost no oscillation from the wrist or fingers. And now I turn the stimulator off, and you can see this even more. The amplitude is much bigger, but again, the oscillation is coming from the proximal joints. So to really study this type of tremor in great detail, you need motion transducers on each of the limb segments, on the arm, forearm, and hand. So to summarize, so the biomechanics of whatever body part that you're recording from has to be considered when you use these motion transducers and EMG to evaluate tremor. you can't just put a motion transducer on the hand and expect it to accurately measure multi-joint movement. The alternative would be to restrict motion to one joint, artificially restrict motion to one joint, as I showed you in the initial studies of wrist tremor. But then that type of measurement might not do a good job of reflecting the patient's clinical disability. Coherence depends on the degree of tremorogenic entrainment of motor unit activity and central neural networks. So coherence basically tells you to what extent these pathways have become pathologically entrained by this tremor rhythm, by this tremorogenic oscillation. And then finally, the rhythmicity of a tremor is clearly a function of amplitude and is a reflection of tremorogenic neuronal entrainment. So it's very unlikely that rhythmicity is going to be able to diagnostically distinguish different types of tremor. And in any case, if you're comparing one tremor to another, you have to control for tremor amplitude, which is sort of a surrogate measure of tremorogenic neuronal entrainment. So that concludes my talk. I'll be happy to answer any questions.
Thank you, Professor Elble. Very good. So, eu peço que quem quiser escrever a sua pergunta, faça e eu tento traduzir para o professor Elble. Before the students, if they have some question, they can write and I translate to you. But I have some questions before the students, okay? How do you see the possibility to use sensors inside of smartphones for tremor evaluation?
So the sensors in the smartphones, I think, are very usable. They're, of course, the housing is much larger, so it's more difficult to mount these devices on different parts of the body.
Yeah.
And you have to know what type of transducer or inertial measurement unit. They all have a triaxial accelerometer, magnetometer, and gyroscope. So you have to know the technical specs for these devices.
Of course.
But yeah, I prefer the motion transducers, the individual motion transducers, because they're smaller and they can be mounted more precisely on different body parts.
Of course, of course. And other thing is, in the results you showed results from electromyography, from accelerometers, from gyroscope. If I want to study tremor, what I have to consider, to take in account, to choose electromyography, gyroscope, and accelerometers. And I could see that you choose to show the tremor in x-axis of one of sensors. And the tremor is a very complex movement. And what are your advice to think about the tool and how to analyze them to tremor?
So good question. If all you have is a triaxial accelerometer, you cannot measure rotation.
Yeah.
Accelerometers measure translational movement. So you have to know exactly how far that accelerometer is from the axis of rotation, which may change from moment to moment. Right? It may start out that the oscillation is at the wrist, and if it changes to the shoulder, we have a completely different ball game. So on average, I prefer to measure tremor with the gyroscopic device because it is independent of the axis of rotation, and it measures rotation, which is most human biomechanical movement. If you think about it, even gait is primarily, it's translational motion of the center of mass produced by rotation of our joints, of our limbs. And so in one way or another, if you're actually measuring the motion of these different limb segments, the gyroscope is going to be best. But now with these biomechanical models, well, you've done some work of this type with posturography. I mean, it's amazing what you can accomplish if you use an inertial measurement unit and not a triaxial accelerometer. With a triaxial accelerometer, the most accurate motion measurement is going to be in the vertical direction because the gravitational vector is vertical, and the artifact due to small rotation is going to be negligible.
Okay. So we have one question from Luana. Well, basically, she would like to know about the origin of tremor. I don't know if pathological or physiological, but it is there some center for tremor in our brain. And other thing was in your results, you show especially results from hand tremor. But if the origin of tremor is central or from other region and is irradiated to hand, it the analysis in the hand could be some bias to analysis.
Yeah, so the good questions. The origin of tremor. We know the origin of tremor in the case of physiologic tremor. We're pretty sure of the origin of tremor in Parkinson's disease. Like I said, the oscillation appears to originate in the basal ganglia and then is transmitted to this loop. And in reflex cortical myoclonus, so-called cortical tremor, we know that the oscillations, this broad spectrum oscillation seems to originate in the cortex. Aside from that, we don't know the origin. Yeah. In the case of classic cerebellar intention tremor, due to a lesion in the deep cerebellar nuclei, or in that little girl's in the pathway from the cerebellum to the thalamus, there the oscillation seems to be due to an instability in the long loop mechanical reflex. The cerebellum is important for feed-forward motor control, and when that's lost, the nervous system then relies more heavily on transcortical feedback pathways, and which aren't adequate. And this over-reliance seems to result in this very irregular overshoot and oscillation that you see in patients with cerebellar disease. But in essential tremor and dystonic tremor, we simply don't know where the oscillation originates. It could originate within that loop, within that so-called tremor loop, but it also could originate outside that loop and be transmitted to this tremor loop as it is in Parkinson's disease. We don't know.
Okay. One more question is, today we are living the age of machine learning to solve everything.
Yeah.
And then when you have time series of tremor, independently if it's my electromyography or accelerometers or gyroscope. You can extract dozens or hundreds of features, you see. And how do you see the possible role or the current role of machine learning in the tremor classification or tremor identification in patients or even in healthy subjects?
Well, I'm glad you asked this question. So the machine learning algorithms and so-called artificial intelligence algorithms, they're only as good, the results are only as good as the data that you feed the algorithm, right? So if you record tremor inappropriately, the algorithm is going to give you crazy answers. And I think that's it's my understanding that a lot of these AI developers on the internet, search engine developers, they fight over not the technology as much as the data that they train these algorithms with. So that's the real advantage that Google has, for example. They have an enormous data bank.
Yes.
But it still has to be collected carefully. And there was recently a paper on, I can't remember the authors, but an AI algorithm, a review of AI and machine learning with tremor diagnosis. We've got a long way to go. That's all I can say. And I think it's because measures like rhythmicity, frequency, and all of these things depend so much on how carefully they're recorded.
Yeah, of course.
So to give somebody a motion transducer on their wrist, it's going to give you a very limited measurement of tremor.
Okay, good. So, Professor Rodger Elble, I would like to thank you very much for your time with us. You see, we are completing 1 hour. Some students, they also appreciated our presentation. I hope to have other opportunities to talk with you and to see your lectures and papers. Thank you very much.
Yep. If anyone has any other questions, they can email me and I'll be glad to answer them.
Yes, yes,
Absolutely.
yes. Thank you very much.
You bet. Thank you for an invitation. Thank you.
Thank you.